You know that feeling, right? The sand between your toes, the sound of the waves. There's just something about a beach. But what if they were, well, becoming ghosts? Right now, the sandy shores we all love are facing this huge, unprecedented threat. And figuring out what they're going to look like in the future, that's not just some academic puzzle. It's one of the most urgent challenges we face.
So, let me ask you a personal question. Will your favorite beach still be there in 50 years? It sounds dramatic, but it's a very real question. You see, with sea levels rising, the future of countless beaches is just hanging in the balance. The problem? Predicting which ones are going to make it and which ones might just disappear is incredibly complicated. And it turns out, the tools we've been using for this job, they have a major blind spot.
For decades, the way we tried to predict this was pretty simple, maybe a little too simple. We relied on these one-size-fits-all rules, but the coast isn't simple. The new reality is that it's this incredibly complex dance of interacting forces. Think rising water and moving sand. And our old models, they were missing most of the steps in that dance.
Okay, let's dive into why this is such a tough nut to crack. And to really get it, you first have to understand the sheer scale of what we're talking about.
We are not talking about a few beaches here and there. The research is crystal clear. About one-third of the entire planet's ice-free shoreline is sandy. And all of it is on track for what they call significant long-term transformations. So, if the problem is that massive, why have our predictions been so off?
Well, a big part of the problem was a classic tool called the Bruun rule. For a long time, this was the go-to method. It basically assumed that as the sea rises, the beach just migrates. It kind of shifts up and inland, keeping its shape, almost like it's riding an escalator. But here's the thing. That's just not what happens in the real world. That simple idea completely misses how the beach itself gets reshaped and scoured out by the constant force of the waves.
To really get this, we need to break it down. There are basically two fundamental forces at play here, two main ways that sand moves on a coast, and it's how they work together that paints the full picture.
First, you've got something called cross-shore transport. Just think of this as the up and back movement of sand, perpendicular to the coast. This is the force that makes the beach march inland and upward as sea levels rise. It's the escalator part of the story. But then, you have this. Longshore transport. And folks, this is the absolute game changer. I want you to picture a river of sand that flows sideways, parallel to the shore. It's created by waves hitting the beach at an angle, constantly pushing sand down the coastline. This river is always moving, feeding sand to some parts of the beach and starving others.
And right here, this is the core of the challenge. You can't just look at one or the other. That inland march and that sideways river of sand, they're happening at the same time, constantly messing with each other. And predicting that complicated long-term dance, that's been the holy grail for coastal scientists.
And this is where the breakthrough comes in. To finally solve this puzzle, scientists developed a totally new way of modeling this stuff. It's a framework called LXT, and it was designed from the ground up to simulate this complex dance over decades, even centuries.
So how does this thing see the full picture? Well, the secret is that it's not one model, but two, working in perfect sync. You have one part that's looking at the coast from a bird's-eye view, tracking that river of sand. At the exact same time, another part is looking from the side, tracking how the beach profile moves up and back. But the real magic, the secret sauce, is that these two models constantly talk to each other. They share data back and forth to build a single, complete 3D picture of how the coast is changing.
Now, a fancy new computer model is one thing, but does it actually work in the messy, real world? That's the million-dollar question, right? To find out, the researchers took it to a really challenging test site on the coast of France.
The spot is called Lacanau in southwest France. This is a high-energy coast, meaning it's just constantly getting hammered by powerful waves from the Atlantic. But what makes it the perfect laboratory is this. A big chunk of it is armored by a massive seawall. It's the perfect place to see what happens when human engineering goes head-to-head with the raw power of nature.
So here's what they did. They set the model to run 90 years into the future, all the way to 2100. They threw a high-end,
kind of worst-case scenario for sea level rise at it to really put it through its paces. And, this is super important, before they looked into the future, they tested it against a decade of real-world data from the past. And guess what? The model's predictions were spot on.
This really gets to the heart of why this new approach is so important. An old model might see the shoreline changing shape, but it's blind to how the beach profile itself is getting scoured away. Another model might see that profile change, but it completely messes what's happening to that river of sand. Only the fully coupled model, LSX-ST, sees the critical feedback between them. And it's in that feedback loop that they discovered something, well, something pretty alarming.
The model showed them something that would be totally invisible to us for decades. It turns out the seawall, the very thing built to be a permanent defense, was actually creating a hidden, dangerous tipping point way off in the future. Here's the timeline the model laid out. For the next few decades, everything looks kinda okay. The erosion is pretty much the same everywhere. But then, around the year 2065, something changes. A trajectory shift happens. The whole system hits a tipping point. And by 2100, the coast just south of that seawall is eroding at a shocking, accelerated rate. And the numbers, they are just stark. By 2100, the model shows the beach on one side of the seawall retreating about 110 meters. But the beach on the other side, it gets absolutely hammered, retreating a massive 230 meters. That is more than double the erosion. So what on earth is going on?
Well, it all comes back to our river of sand. See, as the whole coastline slowly erodes, the seawall starts to stick out further and further into the water. Eventually, it starts acting like a giant dam, totally blocking that natural flow of sand. So the beach on the other side, it's cut off from its food supply. It's starved. And a starved beach begins to waste away at a catastrophic rate.
So let's zoom out here, because this is way bigger than just one model or one beach in France. This discovery, it forces us to completely rethink our entire strategy for how we protect our coasts.
And here it is. This is the central, pretty sobering takeaway. The very structures that we build to save our beaches, the seawalls, could actually be putting them at a greater risk of going extinct. By locking them in place, by stopping their natural retreat, we might be accidentally setting them up for a total collapse down the line.
And if you're wondering just how many people this affects, look at this number, 40%. That's roughly the share of the entire world's population that lives in coastal regions. The fate of these sandy shorelines isn't just about protecting a nice place to go on vacation. It's directly tied to the homes, the cities, and the livelihoods of billions of people.
So we're left with this really powerful and really difficult question. This research shows that the consequences of the choices we make today might not show up for decades. So if the very defenses we build can create these hidden tipping points, well, that changes everything. It means we have to look past the easy short-term fixes and start asking a much harder question. What does true long-term resilience for our coasts actually look like?